As energy needs expand, and the quest for abundant, sustainable energy sources increasingly turns to fusion, the small aspect ratio tokamak, SMART, represents a significant step forward. The first plasma has been achieved recently by this experimental fusion device, an incredible milestone developed by researchers at the Plasma Science and Fusion Technology Laboratory of the University of Seville. SMART, unlike the traditional tokamak, investigates the unprecedented idea of negative triangularity, a configuration that could revolutionize the energy efficiency of fusion. But what does this mean for the future of energy production? Tokamaks, donut-shaped machines designed to keep superheated plasma stable, depend on these carefully ordered arrangements to stay stable. Upside down, plasma has traditionally been positive triangularity, in which its D shape has its curved edge facing outward. However, recent research has found that reversing that configuration produces a negative triangularity shape, which can greatly mitigate instabilities. These so-called edge-localized modes, ELMs, lead to a regime of instabilities, posing a significant challenge to reactor walls to curb the plasma. SMART is the first compact tokamak intentionally designed to investigate the advantages of negative triangularity. The expectation is that this shape of plasma will suppress ELMs, resulting in better plasma confinement for longer periods at higher temperatures, like this artificial sun, which is 100 million degrees and has a strange effect. SMART can produce plasma of varying forms, so this flexibility will make SMART an invaluable tool to test and validate this theory on a practical level. The importance of negative triangularity is more than academic. This configuration has already been noted as promising by the U.S. Department of Energy for alleviating instabilities while keeping high fusion performance. If it succeeds, SMART will demonstrate the ability to leverage negative triangularity to stabilize the plasma, potentially allowing tomorrow's fusion reactors to be designed in a way that is more energy efficient and economically viable. The SMART project is far from a gimmick. It is a central part of the Fusion 2 grid strategy from the University of Seville, and an initiative designed to produce fusion energy as a grid-based power generation option. Reaching that first plasma is only the beginning. Scientists at the facility now work to reinforce the device's performance and explore its potential in collaboration with universal colleagues. SMART is also relatively compact while integrating three groundbreaking technological approaches: spherical tokamaks, negative triangularity, and high magnetic fields. Through their combination of these attributes, scientists are hoping to develop the most powerful fusion reactor that can fit into the smallest space. If SMART can deliver, it may certainly usher in the era of commercially competitive fusion power, with follow-up plants that are both powerful and economical. Among them, the SMART project keeps attracting widespread global interest. Even researchers in other countries are eager to work together and develop advancements based on the discovery of the University of Seville group. The scientific community is collaboratively addressing the current state of fusion energy by sharing data and insights, which will ultimately lead to overcoming obstacles such as stable maintenance for extended periods and advanced plasma confinement practices. The milestones achieved by SMART have fascinated the international scientific fraternity. Fusion energy has been regarded for decades as the holy grail of clean power, capable of producing enormous amounts of energy without harmful emissions or long-lived radioactive waste. However, the difficulty has always been keeping the plasma stable long enough to reach the temperatures and pressures needed for fusion reactions to occur. By proving that negative triangularity is advantageous for stability, SMART can significantly advance the design and realization of commercial fusion reactors. Keeping a plasma environment nicely contained and stable is one of the biggest challenges to developing fusion energy, and scientists believe this approach can ultimately solve that problem too. With ongoing refinements and international collaboration, SMART could be a major move toward making fusion energy a viable and scalable answer to the world's energy needs. The potential success of SMART would also be consistent with broader efforts in the fusion industry. Other efforts, including ITER in France and private sector projects, are scrambling for sustained fusion reactions. If SMART's design works out, it might influence future reactor designs, helping create a more diverse and competitive fusion energy environment. The ability to harness NK-negative triangularity combined with compact reactor designs offers the potential of smaller, cheaper fusion power plants for commercial operation. SMART's initial plasma is an important milestone toward fusion energy. Negative triangularity helps improve stable fusion reactions. Researchers' test of stable fusion reactions with new angles brings commercial fusion a tad closer to reality, but full commercial fusion is still quite a bit further out. The University of Seville team will develop SMART in collaboration with global experts to drive the science of fusion. But as energy demand is growing, innovations like SMART offer a glimmer of hope that society can find a sustainable, infinite way to power itself, like the artificial sun, which is one step closer to producing infinite energy.